what we are going to do now is to build a deep neural operator to perform integration. Now, integration will depend on the function we are trying to integrate. Usually, we can perform integration by, usually analytical integration, but also, of course, for any kind of function, what we will do is or what we usually do is we integrate using um, numerical integration. So, in order to train a neural operator to perform integration, we need data. The data has to be generated, and then the base function has to be generated. And after that, what we need to do is we need to integrate this base function and then put all of these curves into a one data for it to be used in the in the deep neural operator training. Because this time we will not rely on physics, we will rely on the data we generate that will be used to fully train the neural operator. So let's do it. We start by importing, or first we start by writing the name of this notebook or the name of this code. For example, it's ordinary differential equation integration main, or become let int main, and then we will import the needed libraries. We start by importing torch, just a little bit here, import torch, and then import torch.neural network as an n, import numpy as np, import for plotting matplot lib.pyplot as plt, and here it will be a little bit non-usual things. We need to create a data that is somehow follow a specific, it's a random, but it has to follow specific Gaussian distribution. So we will use this library called GS-Tools, and we import srf Gaussian, and from GS-Tool import .random, random. Of course, many ways we can do it, but we'll do it same library master RNG. This is going to generate a random number, and then last thing is from scipy import integrate, and shift enter. So these are basically the libraries that we will use in order to integrate the data. Now let's first see what kind of lines we will generate, and later what we will do is we will keep making these integration processes. No module called GS-Tools, not tool, tools, sorry. Now should work. Okay, so now what we need to do is we need to start making the data. We need, in order to make the data, what we have to do is to, we have two things. We have how many curves that we are going to use to train the data, and there's also the points in these curves, how many points of these curves. As we will see, is what we are trying to do is we have a curve that will look like, for example, whatever it is, like this. Let's say like this. Oh, it should not some curve like this, and we will have another curve that represent the the area under the curve or something, whatever, like the, the, the plot of it. So we have the points we have to consider in here, and later what we will have is the curve that represent the integration of this curve. So we start by saying that we have the number of points. We will consider 100 number of points. That is how many points in the curve itself. So we're talking about how many um, lines, or how many basically data point of every curve, describing every curve, and this is going to be 100. And then we will use 110 well, curves, and what will it will look like basically this way. For example, x will be mp dot line space, and this is what we will create is the s and m, and mp dot line space, just like this. Yeah. So if we print this, we will have the amount of points representing this is basically the it's 100 point, and it is changing from 0 to 1. So this is going to be our curve. Now, of course, this is the x, which is we have 100 points, and all of them is from 0 to 1. But in the actual thing, or that this is, we didn't generate a curve itself. We didn't generate a function, and this is what we need to generate. We need to um, create from the x points, we need to create a function. So this we will start by using this GS tools, and we will use master, basically this library, and we will give it whatever like number it is. It's just whatever number, it's going to be our seed, and then we define the function. We call it well, one function, and one function means it will generate, it is a function that is going to it's a function that is going to generate just only one function. So the the way it works is we will have here, we said we have the x, which is 100 points, and then we need a function to generate this like a black line, which represents just just any function, a random function. And this the other graph is going to be the integration of that first function. So what we will do is we will need to have as much as possible functions with somehow random generation for this function in order to create, well, a wide range of data, let's say. So or like a little bit random curves that of course it is random, but it's kind of not very wide, because we are actually setting the range of generating these curves. So the model will be Gaussian with dimension equals to 1, and the variation equals 3, or variance equals 3. That means our data, it will be in a range from, it will change about 0, but in a variance of 3. And then we have another here function, or another sorry, parameter, which is 0.3, and this is This number is the connection, the relation between every point and the other, and this is 0.3 means they are somehow related. The By changing this number, we will change how the function change in more random way or more less random, less connected between every point and the other. There is no relation or there are some relation. So it just controls that the function should be a little bit smooth. So this is where you can change this point. So yeah, so basically this is this model has to be used for the SRF, this one, which is going to generate this curve SRF, and we will add the model. We will add the seed equals all seed, and f equals srf dot structured, and then we add the x that we generate, which is this one, and then we return the function. It's the y0, why put it, yeah. So now we have the function, and again, this is going to generate curves every just a random curve. Let's see how it works. So let's generate some curves. These are curves that we are going to integrate later. np dot zeros, and we will have m and we will have n. As we said, m is the number of points in every curve, and n is how many data points we have. So this is going to be like this, and then yi in range of m, which is the number of curves, and then we will start generating the curves. So we take all the points and then we give it the number of I, indicating every curve. We use this one function and we pass on the actual x. X is not going to change in length. This is one of the things in this data, that x always has to be between 0 and 1. And then we shift enter, and we have a problem. I think it's syntax structured srf. Okay, now it's just srd. I wrote it. It's srf here, this one. So we declared this method, and then we have this the generator of a line within this model. Yeah, and this is basically, we created already the curve, so we can see it. U dot shape. We have 100 lines, and then 1. This is the data point, or 0, starting from 0. This is the first data point, and then 100 values, and then 1. This is the second data point, and so on. So if you want to see these data points, you can just print them, and here they are. Every line, this is of course NumPy array, and every line is a u value, a data point. The whole curve, and we will plot it after this. So if we want to see plt dot plot, and then we plot for x, and we take all the curves and say until the third curve, and shift enter. So these are of course randomly generated curves. All of them will start from 0 to 1, and they will, as you can see, like this, are different curves. Here from 3 we can of course print maybe more. This one is really interesting shape, like it's kind of random, but it's give us a nice shape. So here you can see all of these are data or curves that we are going to integrate. We didn't integrate them yet, but these are going to be the curves that then we will integrate them. So basically, these are all the data points. I mean, if you want to print all of them, you can, yeah, sorry, not like this. You can just write it like this, but it will be a mess. All of these are the curves that we have. So these are the curves. And what we will do is we need to integrate them, as I said. But I think it's just too much curves like this. If we like uh, print them all. So here we can just take and see some samples. So the first thing now we want is we need to integrate them. So we need a function that integrates lines. So def integrate, and here also one function, and it will have the function as an input, and result equals np dot 0 with the size of f. This is 0, like the size of this, and results of 0, the first one will equal to 0, because at the end, the actual thing, the numerical integration, is basically calculating the area. So we start from here, there is no area, there are no areas, so it is 0. We go a little bit here, and now it's more area, and then here more area, and as much as we integrate here, the function should increase. And basically this is the thing. But of course there are some other factors, that there is area that is positive and there is area that is negative. So if it's negative, then we are, well, subtracting some area. So take it in mind, it's not always increasing. If it's all above 0, it will always increasing. But for example, in this curve, the green one, at the beginning we will have increase in area. That means the number will increase, the curve will increase, and then because we're going under 0, it will start to decrease. So this is how area under the curve works. And we will start integrating from 0 to that point, and from 0 to that point, so on. Anyway, let's see how it's done. So to do it, for I in range of 1, because 0 we cannot integrate, is simply it's 1 point, to the length of f, and result of that point will equal the integrate dot sm. This is just a method for integration, and here we will take the value from the beginning up to I plus 1, and this is for f, and for x it will be the same from the beginning to I plus 1, although I think, yeah, we will start from 1. Yeah, it will be from the beginning to one point, one more point, and then return result, which is the whole curve. So what's happening here? We are integrating for all these points, and we said 0 we cannot start, so we start from 1 until the whole thing, until the length of the whole thing, although the length of f, yeah, basically the length of f is it will not, the final point, it will not be included, so we will add a little bit, one more point in here, and we will keep on integrating from the beginning to the we are doing this point, just 1 point before it, to take the whole area under the curve. Of course, some can argue like, oh, why didn't we went to plus 1, we just put it I. It's not gonna make a big difference, and anyway, it's not a neural operator kind of issue. It's more like how the integration works. So this is just integration function, and this is we will shift enter, and this way we are going to integrate the every function. So what we need to do is what should we do? We will take now another function or another data um, kind of envelope or place that we need to put these integrated functions in, same as we did with you. So the first thing is let's make just let's integrate one function at least. Just let's see how it works. So from the whole values of u, which is we said that the values of the curves, we will take only one curve and we call it f, and then f integration for this function, we take it and we pass on the f value, and plt dot plot, we can just plot the integration function and actually the u itself, the function itself. So here we take that function and we see how it goes. We have a problem, results in p not by zeros like, not zero like, zeros like. Yeah. So, or just to make sure. So this is the actual function. It looks like this bell, and the integration of, or this is the integration of the function, and this is the actual function. So this is the integration, and this is the actual function. So what's happening? Or let's understand the data, or not the data, the values we are looking at. The first thing is we start from zero, there is no area, and then as the integration progress, the value here that starts from zero start to increase because this value is increasing. The area under the curve is increasing until we reach to this peaks somehow here, because the area above zero is already increased. After that, what will happen is now we have an area that is below, that is minus, below the zero line. That means the area under the curve starts to decrease, and then it will decrease until we get to this point. That's it. This is how this is the integration of this random curve. Of course, it is a random curve. I didn't really put it looks like a sine function, but uh, this is, we got lucky. We have this beautiful kind of curve, but of course we can just change it anything here we want, and we can just like see how the curves are happening and how the integration is working, the numerical, of course, integration. Now, what we have to do now, what we need to do is the same we did in this thing, the u. We created u, which is a place we will keep all our data that has 100 points, that is the curve, and then 110 data points that are going to be used for training the neural operator. We need to create the integration. So the integration, we call them s, and s will be np dot zeros, and the same thing, it will start from like it will have 100 lines and n number of points. And now we just do the same thing, but this time we will integrate in range of n, and capital S will be everything populated in here, and then the point itself. And then we will take our function that we made, and we integrate what? Integrate the data point we have. So we take the whole points of I, which is the first one, and this is the corresponding integration of every line. Hope it's clear. It's simply we create curves randomly, we integrate that curve that we create randomly, and we store it all in here. So we have u and we have s. U is the input, s is the output that we want the actual neural network to give us. So this way we just shift enter, and it worked. It worked without problems. And then of course the oh, well, okay, let's just print it out. Here you can see, for example, 0. These are the integration of the whole lines, and basically that's it. Like we have the data now is ready, and later what we need to do is we need to take this data and we need to use it for training the neural operator. So in short, so far what we did is create well, numpy array that has lots of curves, 110 to be specific curves, and every curve has a 100 points. And then we have numerically integrate these randomly generated curves into another vector, which is we call it S, and then we kept the data in this S, which has the another 100 points and basically 110 points of data. So this is going to be somehow our X data, the time series, and this is going to be our Y data, which is the result of the resultant time series. So